Okay, this is the same paper, February, March 22, paper 4.2. We have done first 4 questions. Now move to the question number 5. It's already solved for you. The question is the variation with the potential difference V of the charge Q on one of the plate of a capacitor is shown in the figure. So this is the charge on one of the plate and the potential difference between two plates. So straight line passing through the region. The capacitor is connected to an 8-volt power supply and 2 resistors are in S zone. So it means when we have to take the voltage, so we have to take the maximum voltage equal to 8 volt here from the graph. So 8 volts. So 8 is here. And the next, it is connected with the resistor 25 kilo ohm, X and Y, 2 terminals, capacitor, and then 220 kilo ohm another resistor. So 2 resistors are connected. Look at the diagram. The resistance of the R is 25 kilo ohm and the resistance of S is 220 kilo ohm. The switch can be either position X or position Y. So when this switch is connected with the X, there will be a charging of the capacitor. But when it is shifted to this Y, there will be discharging of the capacitor across the resistor S. And the question is, A part, the switch is in position X so that the capacitor is fully charged. Calculate the energy stored in the capacitor. So energy is equal to 1/2 QV. Q is the charge and V is the potential difference, voltage. So area under the graph, this QV graph is equal to the energy. So the area is half base into height. But do remember this capacitor is connected with 8 volt. So you have to take area under the graph only for this 8 volt, not the full area, 8. So from the graph 1/2, the base is 8 volt and the height of the triangle is 1.2 into 10 power minus 4. Mean for this 8, the charge is 1.2 into 10 power minus 4. So after calculation, 4.8 10 power minus 4, this is the energy stored in the fully charged capacitor. And the next B part, the switches now move to the position Y. Show that the constant of the charge circuit is 3.3 seconds, mean it is fully discharged. So this discharging time, full discharging time, mean that this time constant T, the formula is equal to RC, and R is the resistance across which the capacitor is discharging, and C is the capacitance. Now the capacitance from this formula, Q is equal to CV, and C is equal to Q divided by V, which is the gradient of the graph. So the gradient of the above graph is the capacitance. So our resistance is 220,000. The charge is 1.2 10 power minus 4. When the voltage is 8 from the graph, so gradient of the graph, so the answer is to 3.3 seconds. So this is the time constant, mean this is time in which the capacitor is fully discharged. The full discharge capacitor A stores energy E. Determine the time taken for the stored energy to decrease E to E by 9. Look, energy is equal to 1/2 CV square because the capacitance during discharging remains same. So energy is equal to 1/2 CV square. So when C capacitance constant, energy directly proportional to V and V directly proportional to under root of the energy. So the ratio between the voltages is equal to the ratio of the under roots of the energies. The actual formula for the discharging of the capacitor, for the partial discharging, V over V naught, E minus T over RC. This RC is the full discharge time. So V over V naught, this ratio can be replaced with E over E naught under root because we have shown here. And then E is equal to minus T over RC. So original energy, E naught is E. And after some time T, the energy remaining is E by 9. So under root E power minus T over, and the full discharge time we have calculated here 3.3. So E cancelled. 1 by 9 under root is 1 by 3. So 1 by 3 is equal to e power minus t over 3.3. By taking the ln log both sides, this ln 1 by 3 is minus 1.0986. Multiply with this 3.3. The time is minus cancelled. So the time is coming approximately 3.6 seconds. Now, the next part is C. A second identical capacitor is connected in parallel with the first capacitor. State and explain the charge of any to time constant of the discharge time. Look, when three capacitors are connected in parallel, their capacitance increases. When identical capacitor is connected in parallel to the first, it means the capacitance becomes double. And the time constant, mean full discharge time, is RC, C remains same. So T directly proportional, this R remains same. So C becomes double. When C becomes double, the time of discharge becomes double. Thus, time constant will increase and it becomes double. So resistance is constant. So the time constant is directly proportional to C. Due to parallel combination, capacitance becomes double. So the time discharge constant becomes double. So this is the question. I'll move to the next question. Same paper, February, March 2022, paper 4.2, and this question number 6. A small solenoid of the area of the cross-section 1.6 10 to the power minus 3 is placed inside the large solenoid of the area of the cross-section 6.4. So it is 4 times the area. The large solenoid has 600 turns and is attached to a DC power supply. Look, this is DC power supply to create the magnetic field. The small solenoid has 300 turns. Compare the magnetic flux in 2 solenoids. Look, the magnetic flux phi is equal to BA. Due to this DC power supply, the B flux density is constant. So the phi depends on the area, directly proportional to area. In small solenoid, the magnetic flux is small because its area, cross-sectional area, is small. Now, the number 2, the B part is compare the magnetic flux linkage, and magnetic flux linkage depends on the number of turns of the coil. So N phi depends on the number of turns of the coil. Small coil has a large number of turns. Look here written 3000. And the large has 600, but the flux linkage depends on the number of turns. So the small coil has large number of the turns. So the magnetic flux linkage is large in small coil. Yes, its flux is small, but the flux linkage is large. So A part is about the magnetic flux only. And the second part is about the magnetic flux linkage only. So the magnetic flux depending on the area, and magnetic flux linkage depends on the number of turns of the coil. And the next is state Lenz's law of electromagnetic induction. Direction of induced EMF, induced current, is opposite to the source causing it, producing it. This is the Lenz's law. Now the next part is the terminal of the small solenoids are connected together. Terminals of small mean the short circuit. The small solenoid is then removed from inside of the large solenoid. With reference to the magnetic field, explain why a force is needed to remove the smaller solenoid. So when the small solenoid is removed, there's a change of flux on the small coil. And due to the change of the magnetic flux, EMF current is induced in the smaller coil due to rate of change of the magnetic flux linkage. Faraday's law. So electric current, which is induced in the small coil, has magnetic field around it. So there are 2 magnetic fields. 2 fields are in the opposite direction, according to the Lenz's law, because both are opposing each other. So when they are opposite, so their ends are of opposite poles. When their fields are opposite, so the poles are opposite. One has north pole, other has S pole, but there is a force of attraction between north and the south pole. Opposite fields, opposite direction currents, so opposite poles are formed, north and south. So north and south will attract each other. So definitely we have to do some work to overcome the attraction between north and south pole of the both coils. That's why the force is required to remove the smaller solenoid, because the smaller is attracting the larger one and the large is attracting the small one due to the opposite polarity. So this is the next question. Okay, next question, same paper. Alternating current is converted into the direct current using a full wave rectification circuit. Part of the diagram, this circuit is shown in the figure. So complete the circuit by adding the necessary components of the gaps. So look, here is a gap, here's a gap, and we have to draw this one and this guy. And do remember, the direction of the two opposite diodes must be similar. This is drawn already, so we have to draw this one, so same dimension. And here, this is drawn, so opposite, same dimension. This is the point to remember. Two opposite diodes will be of the same direction, same polarity. Next, on the figure 7.1, mark the positive potential output terminal of the rectifier. Suppose we take this terminal positive. For this positive, this is reverse bias and this is the forward bias. So the current is flowing in this direction. When the current reaches here, this terminal becomes positive. This is reverse bias because this side is negative. So the current flows in this direction through the output. So when the current is flowing downwards, so this side is positive, this side is negative. So we have to put here the positive sign. So at the top of this DC output, we have to put the positive sign because the current is flowing downward. Next, look at this. This is the AC power supply. Time at the x-axis and the voltage at the y-axis. Now look at the question. Determine the equation for the V in terms of T, where V is the volt and T is the second. Look, this is sine wave. So for this, the general equation is V is equal to V naught sine theta. V is equal to V naught sine theta. But theta is omega t. So we will write here, V is equal to V naught sine omega t. So V naught is the peak voltage. So look at this peak voltage here. This is 3.5 approximately. And then this omega is equal to 2 pi over time period. So here is the time period. And it is approximately 2.5. So we will write 2 pi divided by time period 2.5 into small t. So this 2 pi over 2.5, you can calculate it. So approximately it is coming 2.51 approximately. So you can write it 3.5 V naught sine 2.51 into T are just 3.5 sine 2.5 T. So this is the equation because we have to write this in V and in terms of the T, mean V naught is required numerically and this omega is required numerically. Now the next part is the supply is connected to a 12 ohm resistor. Calculate the mean power. And the mean power is due to the RMS voltage and RMS current. So for the mean power, we will use the RMS voltage square divided by R because the power is equal to V square by R. And RMS voltage is peak voltage divided by √2. We have written there, peak voltage is 3.5 divided by √2. So this is the value. So the mean power, 2.47 square divided by the resistance, look across which is connected, is given here. It's 12 ohm. So divided by 12, so it's coming 0.51 watt. So this is another question. Now move to the next question. State the formula for the de Broglie wavelength lambda of the moving particle State the meaning of any other symbol used. Look, de Broglie equation is momentum is equal to h over lambda, where h is the Planck constant, and the lambda is the de Broglie equation. But if we write here mvh over lambda, then we have to mention that m is the mass of the particle, v the velocity. So it's up to you. Either write this formula, or you can write this, but you have to mention all symbols other than lambda. For example, momentum, mass, velocity, Planck constant, you have to write their names, okay? And the next question is, electron accelerate through a potential difference, pass through a thin crystal, and then incident on the fluorescent screen. The pattern in the figure is observed on the screen. Do remember, if the electron is in the form of particle, when it is forced to pass through the carbon film, on reaching the fluorescent screen, it will show scattered flashes of light. So this is the particle behavior. But if the electron is converted into the wave nature, when it is forced to pass through the carbon film, on the screen, due to diffraction, it will produce concentric fringes. So here, these are the concentric fringes. It means the electron, the particle is in the wave form, not in the particle nature, it is converted into wave nature. So state the name of the phenomena shown by the electron at the crystal. So this is diffraction. Because electron is converted into wave nature, when it is passed through any crystal, any film, due to diffraction, the fringes are formed. State what is the phenomena shown about the nature of the electron. Due to the high speed, electron is behaving like a wave nature because the diffraction is due to the wave nature, so the electron is converted into wave nature. Suggest why the thin crystal causing the phenomena. Look, for the diffraction, for observable diffraction, the slit separation A or D must be equal to the wavelength, comparative of the wavelength. For the observable diffraction, the spacing between the two atoms, which is behaving like a slit, diameter, it is equal to the diameter. Look, the spacing is this, from center to center. So this is diameter. So the slit separation or spacing between the two atoms is approximately equal to the lambda. That's why there is an observable diffraction on the screen. So lambda either greater than A or equal to A, and A means the D is spacing. It's up to you, either use the A or use the D for the spacing. Now look here, the electron is accelerated through a different potential difference, a new pattern observed, so definitely energy is gained, and the energy is equal to HF and HC over lambda. When electron is accelerated, it gains energy. When energy increases, wavelength decreases. When the wavelength of the incident wave nature electron decreases, according to the diffraction rule, X is equal to lambda D over A. When the lambda decreases, the fringe spacing decreases. Look at this. That's why these fringes are close to each other as compared to the previous. Look, this gap is large, and here the gap is small. Small gap, small wavelength, and small wavelength mean the large or huge amount of energy, and this energy is due to the potential difference. So same explanation here. State and explain the changes that has been made of the potential difference to create the pattern. Look, X is equal to lambda D over A, X directly proportional to lambda, E is equal to HC over lambda, so E inversely proportional to lambda. For small value of the spacing between the fringes, lambda decreases, energy of the electron increases, momentum increases. This large potential difference is provided to accelerate electron. So definitely, to get this situation, potential difference increases, energy of the electron increases, its acceleration increases, wavelength decreases. So when wavelength decreases, spacing decreases. So this is the answer for this.